So it's going to be our notes on chemical bonding. Again, some of this is review, and maybe it'll help you brush up on some of the things you haven't seen for a while, but maybe some of it will even be, maybe you didn't quite get it the first time, and maybe this time it'll stick a little bit better. And we'll be going over this stuff, and we'll be going more into detail on each one of these types of bonds, and hopefully as you've watched the video as well, that this makes more and more sense to you. So let me move this down a little bit. Okay, so chemical bonding is a joining together of atoms to form compounds and elements. So we've been looking at matter, and we know the basic part of matter is an atom. An atom is just a particle that has a nucleus and an electron cloud. And so chemical bonding, let's kind of add some things to this here. I'm going to have to do this, I guess, real quick. Might take a second. I might start over. Probably will. Close. Get out of that. Then I'm going to stop. So it's going to be our notes on chemical bonding. So far we've been looking at matter. And we know that matter is made up of atoms. And depending on what your collection of atoms is, you can have an element, you can have a compound, and you can have a mixture. And so this element, or this atom can give us an element, can give us a compound, and then really these together can give us a mixture. And you should go back and review these in your notes if you're not sure exactly what they are. I might touch on them today, but I'm not positive I'll spend a lot of time on it. But chemical bonding is the joining together of atoms to form these compounds and these elements. So we have this basic part, right? That's an atom. And we then join these basic parts and we get elements and compounds. And then we join those elements and compounds and we get a mixture. So whenever chemical bonding is taking place, we could have the same atoms, and that forms elements. So we might have Cl2, which is really Cl joined with Cl, chlorine and chlorine. So that's an element. We could have oxygen. Oh, a bond here. Usually that line always represents a bond. And these are showing covalent bonds actually, and we're going to talk about that in a minute, but usually these circles represent electrons. And when we see them written this way, this one here, that one there, that one there, and we see them written with a line between them, they're sharing, they're covalent. But if they're the same, no matter what they are, chlorine, oxygen, nitrogen could be this way as well. Nitrogen would actually be a triple, I think, if I'm correct. Could be wrong on that, but yeah, something like that, a double, triple. Off the top of my head, I'm not sure, but we'll check on that later. But the same atom gives us elements. And so the next time is a compound. These are different atoms. So elements the same, compounds are different atoms. So H2O is an example. H2O. And if we were going to write this, we'd have oxygen, hydrogen, like this. And this would also be a covalent. This is one of those polar covalent compounds that we're going to talk about. But that's H2O. They're different atoms. You have a hydrogen and an oxygen. And we could also say NaCl. Now this is a ionic compound. And this joins because sodium has a negative. Chlorine has a negative and sodium has a positive. Those attract each other, they exchange electrons, and they join and form a compound. But they're different atoms, so we call them compounds. And this whole process is really driven by the electrons. They are the joining agent. They are the thing that helps form these compounds. Now, it's also important to remember that the nucleus also plays a role in this. And you probably saw on your, or watched on your video, or noticed on your video, that the joining of electrons also has something to do with the attraction from protons as well. So you have these two atoms that are next to each other, and those proton, that positive charge in both, like if we were looking at H2O here, this center nucleus has a positive charge, this hydrogen has a positive charge, and those also pull on these electrons somewhat to the center. And you have these competing pulls from each one, oxygen and hydrogen, and that results in them being shared. But also remember the repulsion as well. So there's like a balance. So the nucleus of each is pulling the electron, both electrons, but also these electrons are trying to repel each other because they're the same charge, and there's like charges repel, opposite charges attract, and that's the law of charges. It's just true in nature. But the electrons are the joining agent, and they follow something called the octet rule, and that is the full outer shell. And you see that down here, full outer shell, and they try to, however many they're missing in their outer shell, they try to make sure that they're added or subtracted. So it really depends on the atom. So sodium is a positive ion because in its outer shell it has one electron. And if we looked at the atomic number, which is the number of protons in sodium, we would see that it's 11. So the atomic number is 11. And if we were going to just draw the entire Bohr model, and if I started over with this one, I'll show you how this works. So Na, it has 11 protons. It doesn't have a charge right now, so it says 11 protons, so electrons are 11 as well. So then we always know this full inner shell, unless you're hydrogen, every other element has 2 electrons in this first orbital. It's called an s orbital. And the next one, p orbital, and it's really a combination of an s and a p, but it has up to 8. So sodium has 2 to start with, and then it can hold 8 in here, and that gives it 10. But really it has one more. And I'm drawing these together because they do occur in pairs. We're going to learn that when we look at electron configuration. Then you have one more. Okay, and so sodium wants to fulfill this octet role, and it can only do 2 things. It can either take on these electrons, 7 more, can add 7, or it can give away this one, and that's just easier for it to give it away. And really there's other factors in play here. So if this comes near another element that has a stronger pull than this nucleus of sodium, then it can pull it away as well, and it kind of helps it meet that octet rule. But really understanding this octet rule helps us understand what an element's going to do. So the general rule is if it has 3 or less, it's going to give away. It's going to give off electrons, and then it's going to form a positive ion, and then more than 4, I'm going to erase this thing, actually we'll go over here, 4 plus, it's going to take on, and it's going to form a negative ion, and there's the happy medium, the one with 4. So 4, that's only carbon, and there's some silicon as well, but it doesn't give or take, it shares. Okay, and this helps form a lot of these covalent compounds. But we're talking about ions, whether something's going to give or take 3 or less, it's going to give them away, and it's going to form a positive ion. If it has more than 4, it's going to take them on and form a negative ion, anywhere from -3 to -1, give away +3 to +1. And that's kind of the deal. So these electrons, if it's an ionic compound, they are going to give or take to meet this octet rule, and as a result they form ions. Now there's another case. Okay, the other case is carbon, where they can share. So he has the share right here, right? So we have that already. So share, and that means nobody gets it. Like here, they don't form ions. They actually, there's a place where that electron exists where they both have access to it, and that's a covalent bond. Okay, so, but they're both using electrons to combine and form compounds. So I'm going to erase this. And then if we go on here, look at the two types of bonds that we have. Excuse me. They can be shared, and we call that covalent. And this is non-metals only. So this is all the compounds to the right of the periodic table. So like oxygen, nitrogen, chlorine, bromine, potassium, not potassium, phosphorus, I'm sorry, silicon does it, lots of those, everybody on the right, okay, and if it can be non-metals only. If there happens to be a metal in there, then it's something different. It's not a covalent, and these are shared bonds. So no element has control over the electrons. Okay. And then, but they can also be exchanged, and we'll come back to this covalent in a second though. We're going to add something to it. But they can also be exchanged where one takes some electrons, the other one gives, and that's metals. So this is the left of the periodic table. And these are like the alkali, earth, or alkali metals, alkali earth, the transitions, etc. They're all metals. If it has any, if it just one of them is this, then it forms an ion. And they form charged particles, and a cation is a positively charged. So example would be Na. It would form a +1. You would have calcium Ca would form a +2, and then we could even have some of these transitions like iron +3, but it can form others as well. But that's a cation, positively charged. An anion is negatively charged, and these are going to be, for the most part, non-metals. You might say, now wait a minute, you just said non-metals form covalent bonds, but that's only when they're both non-metals. So both elements have to be a non-metal. But if you have one that's a metal and one that's a non-metal, then you're going to have opposite charges. The cations, one of those metals, you know, sodium, calcium, manganese, iron, magnesium, whatever, chromium, copper, those cation, positively charged, could be attracted to a non-metal, such as all these ones we listed up there, nitrogen, chlorine, bromine, and so on. So we'll kind of add these, etc. Lots of them. And within this one is also hydrogen as well. And hydrogen can actually is one of those ones that can be both. It can be an ion, but it can also be a covalent bonding atom as well. Okay, and these form ions. So if you're a metal, if you look at a compound and one of those elements is a metal, we know it's an ionic bond. And we call these ions, but this is an ionic bond. And that means one of the elements is giving away, that's going to be your metal, and the other one's taking, which is going to be your non-metal. And this has to be, and it has to do with the, as we talked before about the octet rule, but also has to do with size. And as you move across the periodic table from left to right, the size of the atoms in the nucleus increases. So when we're comparing like bromine to sodium, bromine's nucleus is much larger than sodium, so it's going to want to take those electrons. It's going to be much easier for it to take them and these types of compounds to form. So not only is it fulfilling the octet rule, but it's also due to size. Bromine is much larger, it can steal those electrons. And then we have something called a polyatomic ion, and this is a covalent bond that forms a charge. An example of this is NO3, nitrate. And nitrate has a -1 charge. Now these elements, nitrogen and oxygen, they're sharing their electrons, but at the same time when they do that, they result with a charge of -1, and some of these are different. There's phosphate, there's sulfate, and we'll learn these. We'll have a little test on these, but they covalently share electrons, but when they do that, they form a charge, and that has to do with when this happens, when nitrogen and these three oxygen share their electrons, some of them are lost. So then, as a result, what they had in the beginning is different than what they had in the end, and then they form a charge because they don't balance out. So one more thing we have to look at. So we have ionic bonds. They form ions, opposite charges attract, and they form a compound. That's only metals and nonmetals form those. One is a metal, the other one's a nonmetal. Then we have covalent. These are nonmetals, only both elements in the compound are nonmetals. But also these have something called a nonpolar and a polar covalent bond. So we have these covalent bonds, and one can be nonpolar, the other one is polar. So polar, we'll go with that one first, is where one element has the electrons closer. An example of that is water, H2O. And that results because of the size of oxygen compared to hydrogen. Now they're still sharing these, but because oxygen is so much larger, this electron gets a little bit closer to the oxygen, and as a result, that makes this region around the oxygen negatively charged, and they call it G negative. And then, but this is a little bit, and there's an area around this hydrogen that's G, or positively charged. So it has like this poles to it. That's why it's called a polar bond. It's kind of like a magnet. You have a positive end and a negative end. And this is actually, I got that reversed. Let me change that. So we have a negative end on this molecule and a positive end. And that's why water is such a good reducer of dirt and other things, because it's polar and it has charges to it, and when it interacts with other elements and such which are ionic, it has the ability to pull them apart, and when we go into acids we'll learn about that. That's a polar covalent bond. But also there's nonpolar, and that's the condition where neither are strong enough, or we'll just say neither are strong. So the electrons are shared equally. So we'll add that. And as a result, there's no poles, no positive or negatives. The electrons are found equally between both elements or atoms. And that's kind of our introductory notes. A little bit long there, I guess. And let me know if you have any questions. Annotate and turn in, and we'll keep moving forward in class. See you tomorrow.